Welcome to our newest statistical test. We are still in the familiar t-test territory. The only difference is now we have what we can call related or within subjects or dependent samples. So now we're talking about people who are the same in multiple samples. So instead of different people in one group compared to different people in another group, that's independent. This is related samples where it's a time one, time two. Has there been a change? In most cases, it's going to be the main question that we're asking for the t-test for related or dependent samples. Let's do a quick review of what came before this. What's the situation for two independent samples? As I mentioned just a minute ago, basically it's where we have different groups and you can't be in both groups. And so those are different populations, and we're seeing if a mean from one group, again, males, females, Democrats, Republicans, oftentimes the easiest examples that come to my mind is there a difference between those two sample means, and can we infer that there's a meaningful difference in the population, different populations for those two groups. Now, we have the related terminology. In this case, a between subjects design is an independent sample. So between groups test is males versus females, Democrats versus Republicans. Within subject, in that case, is within, meaning I have multiple measures within myself. So that means there's a time one and a time two. And has my score changed? Is there a significant difference between the time one and time two scores, or is there not a significant difference? And then finally, what is pooled variance? Basically, when we have two independent samples from the last narrated slideshow, we have two samples, and each sample has its own amount of variability. And we want to average or pool it. And we do that through the pooled variance formula, and that takes into account especially the most normal situation where our sample one, sample two, our independent samples don't have the same n size or sample size. And so the pooled variance takes that into account and gives us a good average, a weighted average if there's uneven sample size. And then we can use that then to calculate our error term or our denominator for our t-statistic. So the same logic is going to apply with our related samples or dependent samples today. But since dependent sample data is different from independent samples data, there's a few things that have to look a little bit different to get to our t-statistic. So here's the basic overview of what we're going to cover. Once again, the steps should look very familiar by now. We just talk about the slightly different set of circumstances or data that we have, and then we move through the different steps in hypothesis testing. Significance test first, then effect size, and then we also have to consider some assumptions that help to affect how much trust we put in the results, or if it's even appropriate to run a statistical test in the first place. So first of all, let's look at an overview of hypothesis tests with related or dependent samples. So again, related samples, dependent samples, sometimes called repeated measures, sometimes called within subjects. I have multiple measures within me. So again, I started it last narrated slideshow and want to continue that discussion of similar concepts, but we have different phrases for them. So independent, between, versus dependent, within, related. So first of all, normally we think of the easiest and most simple form of the dependent sample, which is sort of a repeated measure. I test you once, I test you twice, I test you 3 times sometimes. As we're going to find out, the t-test can only handle a comparison between two means. So if we have 3 or more means, we need another framework, which, hint, hint, it's going to be analysis of variance, or ANOVA, which we'll be coming to very soon. Now what you can also do is, if you don't have dependent subjects data, you can do what's called a matched subject design. And in this case, you have different people in group 1 and group B, but you use a number of factors that you've identified ahead of time to say, well, Joe and Tim are different people, but I know Joe and Tim have the same height and the same weight and the same age, so I'm going to basically match them. I'm going to treat Joe and Tim as the same person because I have enough similarity about them on variables that are important for whatever area of study I'm considering. So you can see that if you're going to do a statistical test involving dependent or assuming dependent samples, and you don't actually have a dependent sample, you have to really be careful about this process and do a lot of explaining to justify that it's appropriate to do this match subject design. So you don't see this very often. I just want to have introduced it here. Now the advantage is you can control confound variables. So if you're doing like a health study, some of the variables I mentioned before, similarity on weight and height and age, you can basically find people who are pretty similar on those and then match them together. So you, in that case, controlled what is potentially a confound or extraneous variable that can affect the primary results or analysis that you're doing. Now, of course, the disadvantage is that you're using a test that assumes dependent measures, time 1, time 2, within the same person, but you don't actually have that. You're just justifying that what you've done is close enough to make it okay to do that. So again, you don't see this very often, but just want to point it out. Now let's look specifically at the t-statistic and going with the assumption that they are truly dependent or the same person over multiple time periods. So here's what we see for sample data. So for example, we see our raw data and we see before treatment versus after treatment. So again, before and after is the classic dependent or related samples design. And essentially we're introducing the concept of a different score, which we haven't really done yet. We're taking one raw score and subtracting it from another raw score. And one thing to point out, it doesn't really matter which way you go. You can subtract, you can do the subtraction with the arrow moving toward the right, or you can do it with the arrow toward the left. You'll get the same D score, you'll get a different sign, but as we're going to find out, you can't get, well, I guess you can get a negative t-statistic, but we'll find out it doesn't really change the interpretation of our test in most cases, as long as we're clear on which is the first one, which is the second one, and we're doing it consistently. So in this case, we're taking the first one, the second one, and then subtracting the first one. So in that case, we start with a smaller score, subtract from that a larger score, and we get a negative D or a negative difference score. And you can see these are 5 people. Now, notice in independent groups, it doesn't matter the order of these numbers within this group or within this group. If these are independent groups, there's nothing linking this score to this score or this score to that score. But of course, now we're actually subtracting one raw score from another. I mean, we can only do that if we know that these scores go together. They're linked somehow, and of course they're linked in that they're the same person. Okay, so hopefully you can see it in the raw data. We can only do this difference score if we know for sure that this score in this row is from the same person as this score in this row. So now we're basically saying with our hypotheses, they look even simpler. We're just saying if you add up all those different scores, and again, we're phrasing our hypotheses at the population level. If you add up all those different scores, they equate to 0. There's no change between time 1 or time 2. And of course, the alternative version of that is that you add up all those different scores, and that sum is not equal to 0. And again, not equal means we are stating a non-directional or a two-tailed hypothesis. If we do a directional hypothesis, we'd use greater than or less than signs here. So the t-statistic basically, for again, seeing how all of our t-tests are related, single sample t, we have one sample mean minus a known population mean. and then over an estimated standard error. And again, we take this estimated standard error because we don't actually have the population standard deviation. We can't do a z-statistic, so in this case we have to do t, estimated standard error. Independent sample t-test, we have now two sample means, one sample mean minus another, and then we have a standard error that represents that difference based on a pooled variance to get to this estimated standard error. And we know the standard error corresponds to two independent samples. Now, in a related, because of the notation here, one sample mean minus another sample mean, how is our related samples t different from that? Now, if we see this subnotation of d, that means we're talking about difference scores. And once again, we don't know our population mean value, so essentially this is 0 when we actually calculate the t-statistic. So the one value we do have is that mean or average of the different scores. And then, of course, since we're in d-score territory, we've taken our raw scores and converted them to different scores. We need a standard error of different scores. So our corresponding standard error is basically our standard error of the mean of different scores. So that's what all those parts of the notation mean when you put them together. How do we get that? We go back to our variance of our different scores and then divide by n to get our standard error. So again, the process is very similar. How do we get from raw scores to means? And that's our numerator of our t-statistic. And then our denominator is how do we get to an estimated standard error. So now let's look at how this goes together into a hypothesis test for our related or dependent samples t-statistic. So as stated before, our null and alternative hypothesis are there is no difference. There is no, if you add up the d-scores, there's no consistent difference between time 1 or time 2. It adds up to about 0. The alternative hypothesis is that it adds up to something significantly different from 0. And again, we're thinking about that term in terms of our population, and we only have sample data. We only have those different scores from actual sample statistics, but we're going to use that sample information to infer about the hypothesis and the population specifically in terms of our hypothesis informing us about the population. So then we need to set the decision criteria, and here's where we select our alpha value. Usually the default is alpha 0.05. So if we need to set a more restrictive alpha, we're more worried about a type 1 error than usual. We want to have a less likelihood of making a type 1 error. Then we go to a more restricted alpha. We move from alpha 0.05 to maybe an alpha 0.01. But the default is usually alpha of 0.05. We have a 5% chance of making a type 1 error if we reject the null hypothesis. Also, if we look at non-directional or directional, the default is non-directional or two-tailed test. We also have to think about our degrees of freedom, and then we have to go to our t-table, and we can use the same t-table that we've been using for the other t-test, and then we locate our critical region, and that sets our cutoff values for our t-statistic, and if our t is larger than our cutoff value or falls into the critical regions, we reject the null hypothesis that there's no difference, that instead the alternative hypothesis that there is a difference between time 1 and time 2. There is a significant change across time. Then we go to step 3. So here's where, once we've set our decision criteria and we have our null distribution set up, then we find our MD, or our mean of the different scores. Then we can take those different scores and sort of pretend like they're raw scores in terms of calculating our sum of squares and then our variance, and then the square root of that divided by n to get our standard error. And again, it's the standard error of the mean of different scores. Is there a big standard error, a lot of variability of the mean of different scores, or are they close to the same values? There's little standard error of the mean of different scores. Then we just calculate our t-statistic. We take our mean of the different scores on the top. If that's big, that's likely to lead to a bigger t-statistic. But if this is big or small, that's relative to how much error or noise compared to our signal we have. If the noise is big, our result we're less sure of is smaller. If our noise is small, our result is more clear and we're more sure if we make a decision. And that decision, of course, is either to reject the null or to fail to reject the null hypothesis. So let's work this out in an example of the raw data. And of course, now we have a dependent samples. Person A has raw score before treatment, raw score after treatment. Is there a difference? And we see there's a difference. It's gone down. And for most of the people in this sample, we see the difference is that the before score is higher than the after score. And of course, that's not universal because one person actually went a little bit higher. Most people got lower by a larger amount. And so then our average of the different scores becomes -6. Now it's important just to think, what does this mean? Well, once we calculate our d-scores, we have to be consistent. Either we're subtracting after, and we take our after and then subtract our before, after then subtract before, or before and subtract after, before and subtract after. So when we interpret our MD, our mean of difference scores, we have to look at the raw data, or at least be familiar with it to know that before is generally higher, after is generally lower. And so that's what's telling us what's going on in the numerator of our t-statistic eventually. Then think about what happens with our variance and our standard deviation and our standard error. So think about going back to exam 1 material. How do we calculate standard deviation? Well, we start with, in some ways, we're just treating these d-scores as raw scores, and we want to get a measure of variability of these scores. We already have our central tendency, our mean of these scores, but now we want our variability. So then we calculate deviation scores. Our raw score minus our mean, x minus m, and that gives us our deviation score. We have to be very careful with the negatives here. We're taking a -8 minus a -6, which is a little ugly. But then, for example, we can go to our deviation scores for each person. They should sum to 0. And again, that's a problem. It means we got it right, but it's a problem because it's not a meaningful metric if deviation scores always equal 0. So then we square those deviations. We add those square deviations up to get sum of squares. From sum of squares, we can get variance. From variance, we can get standard deviation of individual scores. And then now we're going to put it on a distribution of means. So now we need a standard error for our distribution of means. So all that work, the mean of the different scores is the top of our t-statistic. That's pretty easy. But then we have a whole bunch more work to get our denominator, which is our standard error. But once we get our standard error, we put that in our denominator, and we've got enough to have our t-statistic, and then conclude whether our result is significant or not significant. So now that we've got the basic process for doing our significance test for our related samples or dependent samples t-statistic, we also have to think about our effect size after we've done the significance test. So logic is very similar to the previous t-test. Typically, we're going to go with Cohen's d. And for a single sample t-test, mean difference over sample standard deviation. For independent samples t, now we have two means. That's still our numerator. But now we do essentially the standard deviation of our pooled variance. So square root of our pooled variance. And for related samples t-test, again, instead of our standard error, which can be biased by a big sample size, again, big sample size, smaller standard error, we take a step back to our standard deviation for our denominator, and then we have our mean d over our standard deviation, and that gives us our values to calculate our d or effect size for Cohen's d. And of course, you can also do the percentage of variance accounted for, R squared, and that is using our t-statistic plugged into this formula. Now, for our assumptions underlying the related samples t-statistic, we have a couple things to consider. Some new, some old. So first of all, the observations within each treatment condition must be independent. So for example, if you're doing a drug trial and the people taking the drug are talking to each other. So you got your before measure, which they didn't know each other before they started participating, and they just honestly gave however they were feeling that day. And then the after, well, maybe they've seen each other, they're talking about participating in the study, they're comparing notes about how they feel, whether they're sicker, whether they feel better. Now that independence has been violated because their reports after about how they feel are now somewhat dependent on having talked to each other. So we want each person's numbers or recordings to not have any dependence on the other numbers or the other people within that treatment. So both before, both after. That person just provides their data, and it's not biased or influenced by the other people in the group. Also, we're talking about the difference scores. That's kind of what we're basing both our numerator and denominator for the t-statistic on. We assume that these are normal or close to normal. So what that means is if there's extreme outliers and we have a super positively skewed distribution, most people have very small difference scores, but there's a few with super high difference scores, then we at least have to consider that. And if we think it's still okay to run our t-test for dependent samples, we at least have to, when we're discussing it, say, well, our sample definitely wasn't normal, but we think it was close enough to normal that we still calculated the statistic. But we also want to point out, keep that in mind as one potential reason not to trust that statistic, because we may have come close to violating this assumption. Also, let's look at just the advantages and disadvantages of the repeated design or the within subject design. First of all, we have the advantages. Basically, there's the idea of individual differences, which is people are different. And if we have an independent samples measure boys in one group, girls in another group, well, boys and girls are different in a whole number of ways in terms of aggression levels, in terms of average energy levels, maybe communication abilities, verbal and nonverbal. So boys and girls are really different, and those could factor in or be related to some of the measures that we get. So maybe we're not measuring a person's aggression levels, but that could affect maybe our motivation, if that's a key variable we're measuring. If we say there's a difference in motivation between boys and girls, potentially the individual difference, just one of hundreds probably, of aggression could also be related to that difference in motivation that we really care about. Now, the advantage of the repeated measures is that they're the same person. So that means that you were a boy at time 1 and you're also a boy at time 2. So we know that is the same, and that reduces a source of individual difference error because we have the same people from time 1 to time 2 instead of different people in one group compared to another group. That has the effect of reducing error variance, and we'll see it even more once we get to the analysis of variance discussion. But the idea is if you have the same people in time 1 and time 2, which is you have to for a repeated measure design basically, the potential challenge of different people in one group to another group, boys and girls, Democrats versus Republicans, that's just not even a concern. And so there's less total error, and that error due to individual differences is a lot lower. You have different people, but that's consistent differences between time 1 and time 2. They haven't changed their gender, they haven't changed their age, at least not in a inconsistent way. So that's also a benefit. Now the disadvantages we have to keep in mind. Repeated measure, again, is better for a number of reasons. Less variance that isn't understandable, I would say. But the disadvantage is what's called a carryover effect. And essentially, if time 2 treatment is affected by the time 1 having participated in it. So this is always going to be a potential issue because let's say you have a time 1 compared to time 2, you're basically getting the same questions at both times. And so maybe you're too surprised by some of the questions and can't answer them accurately the first time, but second time you're familiar with them. So maybe you trust your second time measures better because of that. Or you could have the opposite thing, where people are either the first time they're going through the questions and really stopping to think about them, but at times afterward they think, I've seen this before, I'm just going to blow through it. In that case, you trust your first measure better than the second measure. So it's really tough to know if you have substantial carryover effects. There's a number of ways that you would maybe ask participants at the end of collecting the measures you really care about. Ask, well, how hard did you try on this? How much were you paying attention to the questions I was asking? And you can see if there's differences in those from time 1 and time 2 and use that to statistically adjust the measures you care about if you've measured potential confounds like carryover effects. So you can statistically predict, measure, and correct for carryover effects, but to do that you have to acknowledge that they're likely there to some extent, and hopefully they're not big. The other disadvantage of repeated measures is what's called progressive error, and this is where it changes predictably over time. So again, carryover effects, sometimes the first measure you trust more, sometimes the second measure you trust more. Progressive error means generally either it's getting better in a predictable way or it's getting worse in a predictable way. So fatigue especially, the longer a test is, especially the more times you have to do it, you trust time 2 and time 3 and time 4 worse than the previous time because the people are getting tired. But you can work the opposite way, practice effects. Basically, if you're doing the same test, and for example, a driver's test, you do really bad the first time, you just barely fail the next time, and then you pass comfortably the third time. Has your driving gotten that much better, or are you just familiar with the things you have to do on the driving test? And if your driving hasn't gotten much better, you're just showing progressive error. And of course, that is a problem we live with driving tests. You're allowed to take it a few times. Even if we're not sure that you've gotten better at driving in general, you may just have gotten better at taking this test, which of course you can see why that's a potential problem. So anyway, a lot of pros and cons, a lot of advantages and disadvantages to the repeated measures design, but hopefully that you can see the clear differences between the raw data and the interpretation of the statistic between the independent measures and the dependent measures, because those same considerations are going to hold up once we introduce and differentiate those concepts between and within subjects, independent and dependent samples for our analysis of variance, or ANOVA, which is coming up.